Alright, so this should be part 2 of how to maneuver your hands with the right hand rule, which just shows us the direction of things when things get three-dimensional. In electromagnetism, you'll find that things act perpendicular to one another. So right hand rule is just a convention that we use that helps us determine the direction of everything. So here we have, we're going to do number 2 and 3. So we have the force experienced on the current carrying wire by an external magnetic field. So the force, here's the equation, the force that these wires are going to experience is something called the Lorentz force. Lorentz force. L-O-R-E-N-T-Z, force. I know it's really hard to see, I'm sorry. So at first we have a current carrying wire flowing to the right, and we have a magnetic field pointing up on the page. Now we do this a little bit differently than what we did in the part 1 video, which is determining the direction of the magnetic field around a current carrying wire. Now we have a totally separate external magnetic field, and we're trying to determine the net force acting on that current carrying wire, called the Lorentz force, which is going to cause the current carrying wire to accelerate and move in some direction, right? And net force creates acceleration, Newton's second law. So this is a method that I've learned in my life that I think is honestly a little bit easier than other methods. There's multiple ways to do the right hand rule when we're determining the direction of the Lorentz force acting on a current carrying wire or a moving charge. But I like this method the best, so bear with me. So we have the equation IL cross B. What the cross means is you're going to cross your fingers. That's what that literally means. So we're going to point our whole arm. So the first thing you do is determine where you're going to point your right arm, only your right one. It's going to follow a positive current. So you're going to use your right arm. Current in this example is flowing to the right, so I'm going to just lay my hands out to the right. And then I see that there's a magnetic field going up, and my equation tells me that I need to cross my fingers into B, into the magnetic field. So what I'm going to do, the easiest way to do this is flip my palm over, flip my arm over. I crossed my fingers into the magnetic field going up, and I have a force going out of the board. That's the direction of my thumb. The direction of my thumb tells me, just like we learned in class, the direction of my thumb tells me the direction of the Lorentz force. So I can represent that by just being a dot, right? That's how we three-dimensionally represent something going out of the page or out of the board. So once again, arm goes in the direction of the current, and then we cross our fingers into the magnetic field, and we can clearly see that my thumb points out of the board. Now this one, we have current flowing up the board, and we have X's, which means that we need to cross our fingers into the board. We have a force going to the left because my thumb is pointing to the left. From your perspective, it's to the right because of optics. Don't worry about it. Just follow along with me. Write down all these examples in your notebook, and you should see and be able to follow along with me. So force is going to the left, so I'm going to draw an arrow going to the left, label it F. So what this means is that this wire, from our first example, will accelerate towards us because of the force is towards us, right? Wherever the direction of the net force is, the direction of the acceleration is as well because of Newton's second law. And here, since the force is pointing to the left, we know that this current carrying wire is going to accelerate to the left as a result of being exposed in this external magnetic field. Okay, so let's go to this example. We have current going out of the board, and we have a magnetic field going to the left. So I'm gonna point my arm towards you guys, towards the camera, and then I see that the magnetic field has to be crossed that way. So remember, arm, IL, cross into B. IL, cross into B. And I have a force going down. So I'm going to label force down. That's the direction of Lorentz force. Therefore, this current carrying wire will accelerate down. And then our last example over here, we have a current carrying wire flowing into the board. So now our arm goes into the board, but we see the magnetic field is pointing up. So you have to flip and cross up into the board, and we get a force that's pointing to the right. And that is how you do right-hand rule for a current carrying wire in an external magnetic field, and it's actually the same exact thing as the right-hand rule for finding the Lorentz force acting on a moving charge, just a single moving charge instead of a current carrying wire. So let's move on to that one. This is number 3. All right, so first, our new equation, instead of IL cross B, similarly, it's QV cross B. That makes sense since our right-hand rule is going to be the same, like convention of what we're doing. We have our arm pointing the direction of the velocity or the current, right? And then we cross out the rest of our fingers into B. It's the same thing. So we have a similar equation. We have F equals QV cross B. This is also called the Lorentz force. They're both the Lorentz force acting on moving charge or moving charges. That's literally what the Lorentz force is by an external magnetic field. So the way I like to teach this is that if it's a positive charge, you use your right hand. And if it's a negative charge, you use your left hand. That's what RH and LH stands for. So if you're trying to find the direction of the force acting on a positive charge, you use your right hand. And then this is kind of unorthodox, but if it's just easiest way to do it, that if it's a negative charge, if we're exploring the Lorentz force acting on an electron, for example, in a particle accelerator or something like that, we use our left hand, even though it's so-called right-hand rule. Bear with me. Okay, so we have a positive charge heading to the right. I label that vector V, heading into a magnetic field that's pointing into the board. So what I'm going to do is going to lay my right arm, because it's a positive charge, in the direction of the velocity, and then cross my fingers into the board. The thumb is the direction of the force once again, and my force is going up. So I'm going to label just in here that when this charge enters, the force on this particle is going to be up. And actually, as a result of that, when we have an acceleration acting on something that's already moving, what do we get? We get centripetal force, right? So it'll actually curve as a result and have a certain radius of curvature. But don't worry about that. All right, so then this electron or negatively charged atom, for instance, or just a single negatively charged particle, I'm going to use my left hand, not my right hand, my left one, and it's heading to the right, so I'm good with that. And my magnetic field is still pointing into the board. So I'm going to rotate my arm such that I cross my fingers into the board, and the force on this negative object, this negative particle, is down. So it's kind of the opposite of the above, which is exactly what should happen. Therefore, that will follow this path through the magnetic field. It'll turn into a circle or a semicircle. Okay, and then we have another positive charge, except now the magnetic field is heading up the board. So I'm going to use my right hand because this is a positive charge. So you take my right hand and I point it to the right, and I see that it's pointing up the board. So what I'm going to do is I'm going to, see how I rotated my arm like that? Ow, did you hear that? That's my shoulder. Okay, so you're going to rotate your arm so that it's easiest to cross your fingers up, and I get a force that's out of the board. So I'm just going to write F and the symbol for out, meaning that this charge will experience a force out of the board such that you see how these particles will curve on the board. This particle will curve out of the board like this. Like that's what that dot and the X's mean. It means it's the third dimension that can't be represented on this two-dimensional board. That's why we use dots and X's. It's just the easiest way to represent that. And then we have our last example, same example as the one above, except now it's a negative charge. So my first step is going to be determining whether right or left. You say, hey, it's a negative charge. I use my left hand now. I once again point it in the direction of velocity, just like my equation tells me to. QV, cross my fingers into B. Once again, it's up the board. I had to rotate my palm so that my fingers can cross up easiest, and then my thumb is directed into the board. So I'm going to draw an X and label it F. That means that when this negative particle enters the magnetic field, it's going to curve into the board. Literally, it's going to like travel in the third dimension. Sounds so weird to say. Travel through the board essentially and behind the board if we were artists and could draw that. But that's why physicists use dots and X's, because we are not artists usually, clearly. And that is right hand rule. You guys will see like multiple other different methods online. Like sometimes I've seen people use the 3 fingers. I've seen people use 2 fingers and a palm. I think this is just the easiest way for using your whole right arm, your left arm. It really gets you moving, gives you some exercise, and it works. So with that, I will end. Bye.